let's talk about polynomial functions. So polynomial function is a function of the following form. So we have f of x is equal to a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1, and so on. So we're going to keep going down. So we have some number here, which is going to be a non-negative integer. And you can see that the power on the x is going down by 1 all the way until we have x to the power 1 and then x to the power 0. So this part is a constant term. So let me write down these little pieces of information. So n is a non-negative integer. So it can be 1, 2, 3, all the way to, a million, 2 million, any non-negative integer, including 0. We can also be 0 for n. This a n x to the power n, this is called your leading term. Also, this number n, whatever you choose for n, this is called the degree of the function. And it's the largest power of n. Sorry, largest power of x. And this a sub 0 is what we call the constant term. And all of these coefficients, a sub n minus 1, all the way to a sub 0, so a sub n minus 1, all the way to 0, these are real numbers. So they can be integers, they can be fractions, they can be square roots of numbers, could be something like pi. Those we don't really have any restrictions other than they can't have imaginary numbers in them. So they can be any real number. N has to be a non-negative integer, so 0, 1, 2, 3, 4, 5, anything like that. Again, we call a sub 0 the constant term, and the part with the largest value of n, which is just this n right here, this is called the leading term, and we also call n the degree of f. So let me give you some examples of polynomial functions. We've actually seen some already. Here's my first example. Let's say 5x squared minus 3x plus 2. Here, n is equal to 2. That's our degree. So n is a non-negative integer. We go up to 2, and you can see, just like in this form here, that at the highest power, everything behind it, we're kind of going down in power. And you see we have an x to the power 1, and this is x to the power 0. So in other words, this is the constant term here. This 5x squared is your leading term. And we know how to graph this, and we know what it looks like. This is a quadratic. So the graph is a parabola. And in fact, because this is a positive 5, the graph is pointing upwards. Okay, let me give you another example. So just a line like 6x minus 1/2. This is a polynomial function. Here, the power, the degree of n, the degree, which is n, is 1. And you can see that this is the leading term. And this is your constant term. It's a fraction, it's a negative 1/2. And we know what this looks like. This is a line. We could also just have a number. So something like negative 7. Here, the degree is 0. This is only a constant term, and we know the graph of this. This is just a straight line. So these are the ones we've seen already. We've seen another one as well. It was one of these functions we had to memorize. If we let f of x be x cubed, just x cubed, this is a polynomial function. notice that the degree here is 3. And you might be wondering, where are all the other pieces that look, so remember that a polynomial function is in this form. So in here is 3, but all these other pieces, the real number that goes in front is 0. So for something like x cubed, this is the same thing as x cubed plus 0x squared plus 0x plus 0. And you can see that this is in the form of a polynomial function. And we memorized what this graph looks like. It looks something like this. Now let me give you some more general polynomial functions just so you can recognize them. Something like 100 x to the, let's say 25, minus 3x to the 4th plus 2. This is another polynomial function. Here the degree is 25. You can see that I'm missing all of the terms that have a power on the x that's less than 25 but bigger than 5 or bigger, and anything between x to the 4th and this constant term of 2. So I could write it out in that big expanded form. But what you want to recognize when you see a function like this is that the powers on the x's are integers, and they're non-negative integers. And then anything here, like these coefficients, are real numbers. So you could put, instead of this 100, you could put something like the square root of 2. That's a real number. And instead of this 2 here, you could put something like pi. And instead of this 3, you can put a fraction. Let's say something like 10 over 4. So all of these numbers here are real numbers. As long as you don't see an I, and as long as the powers for these x's, they are non-negative integers, then you have a polynomial function. So let me give you some non-examples. Sometimes that's helpful in understanding what a polynomial function looks like. So here is a non-example. Let's say 3x squared plus 2x to the negative 1 plus 7. This takes the shape of a polynomial function. The issue is this negative 1. Remember that the numbers here, these powers, have to be non-negative integers. And this is a negative integer. So this is not a polynomial function. Another non-example would be something like g of x is equal to 5x plus 6x squared plus 3 square root of x, which you can also write this as 5x plus 6x squared plus 3x to the 1/2. So these are the same. So if you see square roots or you see fractions in the powers of x, then it's not a polynomial function because it's not an integer. It's not a non-negative integer. 1/2 is a fraction, it's not an integer. So this is not a polynomial function as well. Something else you might see is something like, let me put a little space here so we don't get the one above it mixed with this one. Maybe something like 9x to the 4th minus 3x squared plus 2 over 5x minus 1. Here, we don't have a polynomial function. We have something called a rational function, and we're going to learn more about these later, or we have a polynomial function over a polynomial function. But when you have fractions involved with these x's here, then it's not a polynomial function. So let's put that here. Not a polynomial function. So fractions are not okay when it comes to if you see these x's. If you have a fraction in the coefficient, that's fine. But you can't have something with an x divided by something with an x. Let's just put it that way. Okay, so I'm going to give you a bunch of different functions, and let's just see if we can recognize if they're polynomial functions or not. So determine if the following are polynomial functions. If they are, let's find the degree, the constant term, the leading coefficient, and the leading term. So here's the first one. 10x to the fourth minus 3x cubed plus x squared minus 5x plus 12. This is a polynomial function. So it is a polynomial function. I'm going to abbreviate that. Notice that the degree here is 4. That's the largest power, and you can see that all the other x's have a degree, have a power less than this degree 4. So we have a 3 here, a 2, a 1, and a 0. The leading term is 10x to the fourth. And the leading coefficient is just the coefficient on the leading term. So the leading coefficient is 10, this number here. And the constant term is 12, this number here. That doesn't have any x's. How about this function? G of x is x to the fifth minus 2. Well, the degree is 5. That's the largest power on an x. You can see that anything involving an x has a non-negative integer power. The constant term is -2. You can see that you could expand this. You could say this is x to the fifth plus 0x to the fourth plus 0x to the third, and so on until you get to -2. This is a polynomial function. And you can see that the leading term is x to the fifth. And the leading coefficient, I'm going to put that, coefficient, is just equal to 1, the number that's in front of this x to the fifth. Here's our next example, x cubed minus x. So this is a polynomial function. The degree n is equal to 3. I'm not sure, did I write the degree for this one? Yeah, I did. You can see it doesn't have a constant term. Or in other words, you could say the constant term is 0. Because remember, the constant term is the part without an x. And this piece has an x, this piece has an x. The leading term is x cubed, and the leading coefficient is just 1. That was everything we needed to find. This one is just a line. And you can see that n is 1. That's the degree of this, the power of this x. N is 1. You can see that the leading term is just x, and the leading coefficient is 1. We can see that the constant term is also 1. And this is a polynomial function. Okay, let's look at the next one. We've already talked about something like this. This is a quadratic, so it is a polynomial function. The leading term is 5x squared. The degree is 2. The leading coefficient is 5. And then the constant term is -7. Let's look at both of these. We have g of x is 12 and h of x is 0. Both of these are polynomial functions. So this is a polynomial function, and so is this one. For this one, we only have a constant term, which is 12, and so we have only a constant term for this one as well, which is 0. And that constant term is your leading term. And the leading coefficient is 12 as well. The degree for both of these is equal to 0, because 12 is the same thing as 12 times x to the power 0, and 0 is 0 times x to the power 0. So you can see the highest power on x has to be 0. Okay, let's look at some other examples, and here are our non-examples. You can see I have x to the 1/2 plus 2. This is not a polynomial function. And for this one, q of x, this is not a polynomial function. And y, this one has a power of 1/2. This one has a power of -2. So both of those are not non-negative integers. Here, I have the absolute value of x minus 3. We didn't talk about this one, but writing the absolute value of something, you can't write it as x to a power. So this is not a polynomial function. So if you see absolute value signs with an x in the inside, it's not a polynomial function. And here's an example of a function that has a polynomial over another polynomial. We talked about this. When we have a fraction involving x's, then it's not a polynomial function. Okay. So one thing we're going to work on, what we want to do in the next couple of sections, is we want to graph any polynomial function. So the graphs of polynomial functions are really nice. One thing is they're smooth graphs. So when you draw a polynomial function, you'll get something like this, where you just have nice smooth edges. Maybe something like that, where all of these are like rounded edges here. So they're smooth and they're also continuous. And continuous means that you can draw your graph without picking up your pencil. So let's write that. So in other words, there's no breaks in the graph. No breaks and there's no gaps or jumps. And what I mean by a smooth graph is there's no sharp turns or cusps. So no sharp turns or cusps. So let's think of some examples of polynomial functions we already know. So we know a line, right? Let's give an example. Y is equal to x. This is a polynomial function, and we know the graph looks like this. So we can draw this like a straight line. So it's a smooth line, and it goes on forever. So you could draw the whole thing without picking up your pencil. If you have something like y is equal to x squared, that's a polynomial function. We know that looks something like this. It's a parabola. When we turn, we make a nice smooth turn, and we can draw it without picking up our pencil. Same thing with y is equal to x cubed. If we draw this, we get something like that. But if we draw something like y is equal to the absolute value of x, which I told you was not a polynomial function, if you drew this, it is continuous, but it has a sharp turn. A cusp, I don't know if I wrote that. Yeah, here it is. A cusp is something like this. So it's like a sharp turn, but it's kind of going inward. So this is what we call a cusp. And this is the graph of something like x to the, I think, maybe something like 2/3. So you don't want anything like this, and you don't want anything like this. Something that is not continuous. In fact, we've seen one of them before. I think this is one of the graphs we had to memorize, 1/x. Now here I have a fraction involving an x. We could also write the same function as x to the power -1, which is a non-negative integer. If you were to graph this, you'll get this function here, which goes up forever here and then goes down forever there, and the same thing. So we'll go forever in this direction down here. But in order to draw both pieces of this, I have to pick up my pencil. So I have an asymptote here. This goes on forever. Then I jump and I have to make this graph. So this is not continuous. Something else that's not continuous would be something like where we have a hole. So a graph, or like a line with a hole, or any kind of graph with a hole that's not continuous. And then something else that's not continuous, you could think of something with a jump. So one of these piecewise functions we've defined before, where we have part of the graph like this, and then we have to jump down here or move somewhere else, or we have to actually lift our pencil, that's not a continuous function. So it won't be a polynomial function.